all the difficult, thorny stuff that I haven't wanted to talk about in the first two talks has all been consolidated nicely into this lecture. So this is about measured self-selection and Anthropics and other stuff. I used to say conundra, and then some guy at Caltech got really mad at me and taught me that apparently it's conundrums. Just so so first I wanted to talk a little bit about systems and states in a very general sense. Because I think often people are not entirely clear or careful about what sorts of systems they're talking about. Now, we're used to thinking about sort of closed systems and applying thermodynamics and various arguments to closed systems. I'm going to define a closed system as a system where if you specify the full system at the maximum possible detail at some time, then you get a similarly full description, a complete description of the system at any other time. And that there's a relation, there's basically a relation between those different descriptions. This is sort of often assumed, but usually it's only a convenient approximation. You can pick, a room to be a closed system, but you know that that's not true at all. That there's all kinds of stuff going in and out, electromagnetic, gravitational, all sorts of things. No matter how much you close the box, you're not going to keep out, for example, gravity waves. But I think it is true that space-time and causality can create truly closed systems, even ones that are finite. That is, physics with a boundary that's at infinity, or there isn't a boundary, or where the boundary is null. So, for example, this conformal diagram could be actually, well, that could be either one. So if you take Minkowski space, for example, as a whole, that's argued that that's a closed system by this definition because there just isn't anywhere else to go. You've seen the whole thing, even though there's no boundary to it. You could pick a closed universe where there's also no boundary, but it's a finite system. Or you could take a relativistic system like this diamond, in the sense that if you're somewhere in this diamond, you know that nothing from out here, if you're up here, you know that nothing from sort of out there can influence you, and nothing from down here and that this region can't influence anything out there. And you could show that this gives you everything that if you specify, for example, information here. So suppose I specify the information on some surface like this. Then if I'm up here, everything that I need to know to predict what's going to happen up here is contained in this surface. It can't depend on anything out here because that would have to travel faster than light to influence me if I'm above that line. So you can sort of show that a system like that is closed in exactly this sense. Even though it's true that stuff can leave it, something can go right through that boundary if this is a subspace or some larger space. But it is true that anywhere in that space, you can predict everything that happens given the data that's on some space-like surface here. Yeah?
I don't think this is going to be relevant to the rest of what you want to say, but it's exactly this diamond requirement, the way you formulated it, that Bell-type non-localities are usually thought to violate.
That they violate in what sense?
That if I were to make a measurement out on out over there, okay, it'll produce if I make a measurement on one particle in a singlet state out in the elsewhere of this diamond, it can have consequences which I can't predict from the surface you just described inside.
Well, it won't have consequences. It certainly won't have. In order to make as good predictions as possible within there, I don't have to know about that measurement. Right? So
I don't understand. If you knew about that measurement, your predictions would be better. Because if you didn't know about that measurement, you'd predict that the outcome of the measurement of the spin that's inside the diamond would be 50-50. And if you did know about that measurement, then your predictions would be better than that. They'd be 1 or 0. If you knew the result.
That's actually an interesting point. So the way I've been thinking about this, that is an interesting point though, is if I take the system and write it like this, I can ascribe to the system the density matrix inside. So I've traced out that other step.
Right.
And then that density matrix, that's as good as I'm going to get while confining myself to that system. And I can unitarily evolve that density matrix backward and forward. But that's an interesting point, and I'll think more about that. That there's still relevant information to be had. If you
that would make your density matrix more narrowly peaked.
Yeah,
right.
That's an interesting point. I'll have to think more. So open systems are, we can think of just some space-time region with a time-like boundary so that there's no real way you can play this game without having to augment your evolution equations with some sort of specification of what stuff can come in or out of your system. Yeah.
Can I ask about what you mean by leads to full specification every time? So do you mean uniquely determines the exact full specification at all the times?
That's generally what I'm going to be assuming.
Okay, so you're going to be assuming like unitary dynamics, not like stochastic.
I think I'm going to make that part of my definition of a closed system.
Okay, so yeah, that one is often called like deterministic, so it's closed and deterministic systems.
I'm a little nervous about, okay, you can call it that, yeah. I think not everything is determined in the sense that, your specification will not determine everything. It could be your specification could be a density matrix, which does not determine everything that happens. It's, right?
Reversible might be the better word. Reversible might be a better word.
I'll call it unitary because that's what I mean. So I think deterministic might be applicable, but it might be confusing because I do, it's not, everything is not going to be fully determined even by the full description of it.
Right, but the way the full specification changes is a deterministic process.
Yes. Yeah.
So, with the puzzle diamond up there, you can still have stuff entering in from the bottom.
Right.
Is that stuff that you just then interpret from inside the puzzle diamond as initial conditions?
No, so you say, it depends what so if you specify your data here, then you say, okay, what's happening here? Well, it follows from this data here. That's all I'm saying. So whatever you want to call it, it's something that you can in principle calculate from your initial data, from your specified data here. If you drew your boundary condition here, you could then evolve it upwards and see everything that happens up here, as well as down here, just not past the edges of this.
So it's not essential that the diamond is actually closed in the sense that things can't flow into it from the bottom?
Not at all, no. They certainly can't. Yeah.
Just want to check, the talk of sort of influence and correlations being a little bit around here. That's kind of curious. My main concern is about sort of putting out information correlations.
Yeah, the idea that I'm trying to get across here is that certainly the information is preserved from one, that there's a series of times, and that once you have all the information you're going to get about one time, that information is preserved to the future and the past within that closed region. There's
you
no.
don't make any further claims about causation or influence or anything like that based on this yet?
I don't think so, no. Yeah, I don't think so.
Still just saying, with the diamonds, if causal influence is conferred through the bottom of the diamonds, doesn't that mean that if I specify, say, the system by giving your time anywhere in the bottom half of the diamond, that I don't specify the rest of the diamonds? So, influences could come in like, it's in your initial order.
So if I specify this, then I've specified everything out to this boundary.
Oh, sorry, the time like hypersurfaces. So the hypersurfaces are addressed in always like hook onto two cyclones.
Yeah, that's part of the construction.
Okay, sorry.
So I'm not going to go into this construction in detail because that's Aguirre all 2014. and it's not really done, but the basic idea that I think is true is that we can think of it.
Yeah, sorry, I was misunderstanding the pictures.
So suppose we have some system. Generally, now I want to think about a closed system. And I want to attribute some phase space to it. We know that we can think of phase spaces of systems as being continuous, like particles in a box that have a continuous family, continuous values of the positions and momenta, say. It could be discrete or discretized, so quantum particles in a box, or if you just cut up your phase space artificially into little squares, you could discretize the particles in a box. The phase space can also be compact or non-compact. Particles in a box would be a compact phase space if it's finite energy. If it's not finite energy, then you could say that you can have arbitrarily large momenta, say, in the box, and that would not be compact. On a quantum level, you can think of the Hilbert. You can have a Hilbert space that's finite or infinite dimensional, where this will tend to describe the same sorts of systems as the compact phase space here. So, for example, realistic particles in a box with bounded energy. Infinite dimensional ones would be more like non-compact phase space. And Lenny talked about various senses of, well, we've heard about various senses of entropy, but if you combine either a discrete or finite dimensional Hilbert space with a, well, how do I want to say this? Either a finite dimensional Hilbert space or a compact phase space that's discrete or discretized, then you have a finite maximum possible entropy to the system.
Hey, Anthony?
Yeah. You're going to
Don't quantum particles in a box, I mean, if the walls of the box are really rigid, I mean, this is what we were talking about this morning. If the box represents an infinite potential well, say, then that has an infinite dimensional Hilbert space, no?
At finite energy?
It's discretized. Oh, not at finite energy.
Yeah.
Okay, at finite energy. Good. Good.
At finite or fixed or finite, either one. The way you would have an infinite dimensional Hilbert space would be by having sort of arbitrarily high momentum modes. So you kill that with either a fixed or finite energy. Now, very interestingly, it seems that there are not wholly understood entropy bounds to physical systems in the actual world. So Bekenstein derived or postulated this bound on entropy related to the kind of physical scale of the system, R, its energy, and then fundamental constants, Boltzmann's, Planck's, and speed of light. That entropy has to be smaller than this quantity. And the reason he did that was that it was sort of, it was believed at that point, already since the early 70s, that you could attribute entropy to black holes, the entropy being proportional to the area of the black hole. And if you don't have an entropy bound like this, then you can imagine something that has some enormous entropy. You throw it into a black hole, it makes the black hole a little bit bigger, and the increase in entropy of the black hole is not sufficient to account for the loss of entropy in your object that you threw in. So that would violate what Bekenstein called the generalized second law of thermodynamics, that is one that includes black holes. It would say that you can arbitrarily decrease entropy by having a little black hole, having some big, highly entropic thing, and putting it in the black hole. Right? And then you lose entropy. So if we want to preserve the generalized second law, Bekenstein said we need some bound on entropy of systems in general, to keep the world safe for that second law, then this is the one that he proposed. And that does appear to indeed work for saving the generalized second law. What this suggests is that if you have some finite region of space and you specify some finite energy, that it has this property, that it has a finite maximum entropy or a finite dimensional Hilbert space. And this is, the actual world that we're talking about, if we're going to keep the generalized second law. Now, Bousseau, so there's some things that are a little bit unpleasant about this definition. One of them is that R is a little bit vague, like how do you measure R in a relativistic system and so on. Something that Bousseau derived, well, he postulated, I guess, is a relativistic entropy bound, which says take any sort of compact region of space, like represented by this circle, this surface here, and form incoming light sheets from the boundary of it. So you take your region of space and you send these light sheets in, both in the future and in the past. So you make this kind of double cone structure in space-time emanating from your surface. Now you can, a thing that you can carefully define relativistically is the total amount of entropy that passes through one of these surfaces. So you can think of a sort of entropy flux, and you can integrate that along the surface and add up the total amount of entropy that kind of intersects this null surface. And what he postulated is that that entropy is bounded by the area of this surface. Now, normally you would think, if you just naively wrote this down, you would think that the thing would come out of that is the volume of that surface. Surface is meaning a three-dimensional surface in this instance. So it's some region of space. Right? So you would think it would be the volume because entropy is generally additive. You would think I have some entropy here, some here, some here, so I add the three up to get the entropy of this region. And if I keep going, the amount of entropy I can put in something should be proportional to its volume. But black holes already tell us that that may not be the right way to think about it, since their entropy goes as their area. And here he shows that that's more general, that the bound on entropy has to do with the area of a region of space rather than its volume.
Anthony? Yeah. So this is a bound on the total entropy inside the diamond?
No, this is representing a volume
right
at some time.
Right.
This is a light sheet.
Right.
And you can think of, you could integrate the total entropy in this volume here, but that's not what the boundary is on. It's integrating the entropy along this light sheet, meaning if you have some entropy flow vector, some 4 vector representing the flow of entropy,
right,
you integrate it along that light sheet, and that's some total entropy. That's the entropy that's bounded by this Bousseau bound.
But so it looks prima facie surprising because as long as the sheet, not the light sheet, as long as the surface has those endpoints, no matter what its shape is, the flux through the light sheets is a way of calculating its total entropy.
Pretty much,
right?
Yeah. So you really are bounding the entropy in this volume, but just the construction uses these light sheets to do it. It turns out I think essentially technical reasons, this is the nicer way to do it.
Even though the volume of that thing could be, if the thing were straight, its volume would be smaller than if it were very wavy.
Your upper bounding is
right.
Oh, I see.
Yeah.
Oh, okay. Okay.
Yeah,
You're not saying it's equal to that.
No. It's a bound.
Oh, it's an upper bound. I'm sorry. Thank you. Good.
Is this? Sorry. Go on.
This is the covariant.
Yes.
And is this relevant for consideration that you do with the holographic principle? I've heard that this was sort of developed for the purposes of furthering considerations having to do with holographic. And if you go into the holographic principle, you have to go into the covariant.
Which holographic principle do you mean exactly?
So I'm not sure.
Yeah. Okay.
So,
It probably is the answer in that case. So I'm not sure. Yeah, we'd have to talk about exactly which version of Cruz holographic
There's some
principle. People mean different
That
things.
goes by the title holographic principle.
And it probably has something to do with this, but we have
This is
to.
a historical question.
So in this version, is it fair to say that if you interpret the upper hat as the event horizon, that the Busso bound upper bounds the amount of entropy that could exist inside the region bounded by the event horizon?
Yeah, I think that's a reasonable thing to say. And the effort was to try to avoid questions like, it's so that if you didn't know about this surface, if you just knew about its boundary, right? Then it's so suppose you want to say how much entropy is there in this inside this surface. That becomes ambiguous because it depends on the time slicing, right? So this is a way to give something that's unambiguous by creating these sheets out of that surface, rather than having to specify what this volume is.
So I had them on Busso's holographic.
Even there, I'm not I'm sure exactly which. I mean, maybe let's talk later about a specific thing he's proposing, because in some sense, one thing you may mean by that is the idea that I have this region, and I really should think of the stuff out here as in some sense not existing, that it's really just some re-description of the stuff that's in here and on the horizon. So there's a version of the holographic principle like that. And getting people to say precise words or discern what exactly they mean by that is difficult, I found. So Tom Banks has a rather strong version of that where he explicitly says it really doesn't exist. It's, you shouldn't think about it like that. Rousseau, I think, says kind of it exists, but you don't need to think about it, so why do you? And
Okay.
yes, I think it's related to this.
Okay.
Now, close systems, we generally, though we don't have to, but generally in physics we do, assume that they have some unitary evolution operator. And as we discussed earlier, I kind of put this into my definition. Often it preserves the phase space volume. Open systems may or may not approximate this. Now, if we have this kind of, if we have a phase space volume preserving evolution operator, then we have something like a preservation of the fine-grained entropy, like the von Neumann entropy or the Gibbs entropy. And then we may have, there's a general set of questions, but I think some general understanding of how we can get an entropy that's coarse-grained that will be non-decreasing. Okay, so I'm not going to go into the, nitty-gritty of that. I'm not really going to care that much about this. I'm just sort of going to grab it. Now, an interesting thing that will be relevant for some of the stuff I want to talk about is that if we have one of these systems that's measure preserving and has a finite maximum entropy, then the Poincaré recurrence theorem applies. And so if a system lasts long enough, it's eventually going to return arbitrarily close to its initial state. Now that, in turn, gives rise to the first paradox, the infamous Boltzmann brain paradox. If you haven't heard of this paradox, then count yourself lucky. Because that means you haven't wasted too many hours of your life talking about it with people. I'm not one of those people. I've wasted too much time. But let me explain to you what it is in case you don't know, so that when people say this, you have the right paradox in mind. So the idea is, as I would phrase it anyway, is you consider some system like the one that we've been talking about with a finite entropy, finite maximum entropy that starts away from equilibrium at some macro state, which I'll call A naught. It's going to evolve that way in time. And it's natural evolution, as we talked about. So this entropy is the coarse-grained entropy, the one that obeys the second law. Its entropy is going to tend to increase and go to equilibrium. But we know that the second law is a statistical law. There will be fluctuations away from equilibrium, represented here. These are, and the ones like this are incredibly exponentially rarer than the ones like this, which is not depicted here because I don't have an exponentially large piece of paper. So now suppose we're an observer and we're looking at this system, and all we know is that there's some values, there's some data D that we observe. It's not a complete specification of the system, it's just some data that we observe about the system. And then we'd like to make some predictions based on this data and our theoretical model of what happens in the future. So this is, a common problem in physics. We know we have our physical laws, we have some data, and we want to make predictions about the future. Now the problem is that if I just say, okay, let me look at where the system is compatible with the data D, there's 3 places in this diagram, here, here, and here. All I have is data D. I don't have any extra information that tells me I'm at this one rather than one of these. So if I say all I know is that my data is compatible with D, and since I don't have any other further information, I'm going to give equal weight to this possibility, this possibility, this possibility. Then that method of making predictions will give me predictions that are really weird, let me put it that way. That is, things that I will predict, nearly all instances, that is exponentially more instances of D, will correspond to macro states A that are part of fluctuations away from equilibrium, like these, rather than this one that evolved from something like a past hypothesis, A naught. They will also be, unlike this one, maximum entropy subject to the constraints imposed by D. That is, if D is a room with a bunch of people in it that looks like this, then if that's all I constrain and the rest of the system is a fluctuation between equilibrium, the rest of the system will be some ultra-hot bath of relativistic particles that is wildly in lack of agreement with what we get if we step outside. So our prediction might be, I step outside and it's going to be a nice sunny day and it's going to breeze. I can tell that from the photons reaching my eye from these doors. But if in fact that's all I know and the rest is in equilibrium, what will actually happen if I go out the doors, it will be this ultra-hot blast furnace of free leptons. So simply by opening our eyes and looking around, this argument says we know that we're not in this sort of system. So this makes incorrect predictions, and thus it seems the conclusion is that we do not inhabit a finite entropy Hamiltonian system. Now, so that's the Boltzmann's brain paradox, the resolution that most people take from it. And I'm not going to take issue with this resolution necessarily. I wish I had a good issue to take. Is that the conclusion is that we can't inhabit, in a cosmological sense, a system of finite entropy like that. One of the things that really bothers me about this, and it's the second paradox, is that this conclusion holds for any entropy you like that's finite. So you give me the biggest possible entropy you can come up with, use advanced mathematics to express the number, this conclusion still holds. Whereas if the entropy is infinite, it doesn't hold. And that just seems crazy that by opening our eyes, we can tell something so incredibly vast about the whole structure of the universe as to whether it has a formally infinite maximum entropy or an arbitrarily large, no matter how big a number you choose, entropy. So either that's really, really strange, or there's something wrong with this argument, and I honestly don't know which one it is. Yeah.
Wouldn't another conclusion be that we don't live in a closed system?
Yes. So that was the conclusion, that this argument tells us we don't live in a closed system like that. I'm taking issue with that logic of reasoning because it seems like it's very strange that we should be able to learn such an incredible thing about the physical world just on first principles.
Why?
If it doesn't seem strange to you, that's fine.
Okay.
Yeah.
But look, it seems to me that there are ways of taking issue with the original argument. Okay.
Okay.
Suppose, a bunch of us were just discussing this at lunch as a So we were in the same hell you just described. So in order to, here's the structure of this argument. I take myself to have good reason to believe, say in the Boltzmann case, I take myself to have good reasons to believe that classical mechanics is true. Okay? Classical mechanics, together with finite total entropy, blah blah blah, entails that there will be lots of brains in my current psychological state. Okay? But which shortly thereafter will discover all kinds of differences. Therefore, the right thing for me to do is to put a uniform probability distribution over my being any one of those brains, and that makes it very likely that I'm one of the brains that's in one of the smaller fluctuations. Okay? That in turn makes it very likely that all my memories of the experiments I did and heard about, by which I concluded classical mechanics was true in the first place, never occurred. Okay, so the reasoning leads from my believing that I have good reason to believe in the dynamics in the first place, to my believing that I don't have good reason to believe in the dynamics in the first place. There's something incoherent there. There's something self-undermining there. That is, you could take a different attitude. Okay. Insofar as I think I have good reason to believe that the dynamics is true, I'm already assuming that I'm not one of the Boltzmann brain fluctuations. And so it was wrong of me to then evenly distribute my probabilities over all the Boltzmann brain.
This is going to be a long discussion. So
Okay.
yeah, well, maybe we shouldn't have it now.
Okay.
But maybe later.
Sure.
Because we'll take all these people to hell with us.
That's the idea.
Okay, so that is the paradox anyway. I, for one, don't understand exactly how to think about it. So that's one sort of issue that comes up where it seems to me like the methodology, the sort of setup and the methodology of thinking about observers who open their eyes and counting them and so on gives us results that we have to be very wary of. And I'll stand behind that statement. Now I'm going to take another tack and back up to the idea of not sort of an infinite and uniform in time system, but one that's infinite and statistically uniform in space. Now, in my talk on eternal inflation, I argued that these generically arise within eternal inflation in the sense that the post-reheating region, where inflation stops and the universe gets filled with particles and so on, are generically infinite, spatially infinite. And the properties of those regions are determined by two things. The field evolution, so that sort of says, how the field gets spit out here at reheating. So to say the amount of the metric fluctuations and so on, and the amount of stuff that's there are going to be determined by the field evolution, the metric fields and the scalar fields as they evolve. But there's also this random component provided by the thermal and quantum fluctuations. However we understand the foundations of how those get imprinted, they are there, unquestionably, as you see them. Now the physical laws, essentially there's nothing to break the statistical uniformity of this surface. The surface itself has symmetries of, say, the space-time curvature is symmetric before we talk about the perturbations. The perturbations have symmetries, and the physical laws don't pick any preferred position along here. So I think you can argue that the actual state that comes out here, that say the actual pattern of density fluctuations is statistically uniform in the sense that there's no preferred position on this infinite slice as determined by the statistics. Now there are sort of some subtleties to that, but I think they're not actually relevant for the arguments that I'm going to make next. But statistically uniform is an important one. Now, the paradox that this leads to, which you've all, I think, heard of at some level, is that if we combine this with the earlier statement that a finite region of finite energy has finitely many different possible configurations, then we get this kind of strange situation where this whole configuration here that is in this room is one of finitely many compatible with 100 meters and some finite energy. And if the states that come out of inflation and reheating on this infinite surface are statistically uniform, then there have to be replicas of this exact state in this room. And I think once you sort of got those ingredients, the finite phase space and the infinite statistically uniform region, then that's a somewhat inevitable conclusion that no one has ever convinced me does not follow. How often you will see things just like this room is a totally different question. It depends on a lot of subtle issues, but it's not going to be relevant for what I'm thinking about. And a key point, and this is one that I was getting at in the discussion earlier, is that once you have one of these infinite statistically uniform surfaces, there's no way to label the positions on it, I think, and say, you know, this is point A and this is point B. There's some, if we see this room, then, and we know that there are infinitely many duplicates of this room, there's no sense in saying, in which we can say we're this one, so we're pointing to one on a piece of paper or something like that. We could just as well be any one of these duplicate ones. Was that hopelessly convoluted the way I said that? No. Okay.
No, it wasn't. It was really clear. This is the sort of thing you brought up a couple of days ago, and I thought it was really interesting, and I was thinking more about it since then, and haven't gotten far, but just had the following thought. Suppose that you know you're given the power law of a universe. Then I take it the way you predict. You are also part of the configuration that this that recurs and recurs and recurs. Mm-hmm. And the way to decide, for example, what your brain state is going to be when you open your eyes, okay, is just by applying that power law, like the way you decide anything else. Right? There's no reason at all to think that what you're going to see when you open your eyes has any relation to what's actually in front of you, or anything like that. I mean, the way you decide what your brain state is likely to be is by the same power law. You're among the configurations there. It's a question, does that power law make it likely that the psychological state you're going to be in when you open your eyes has some kind of relationship to what's actually in front of you? That doesn't seem obvious at all.
Right. No, I agree. So that may or may not be the case.
So for example, it's not at all clear whether we could distinguish by opening our eyes between two different claims about what the power law is. That is, sometimes you're talking as if, look, we have these observations, they tell us about a certain power law. If you really take that seriously and think the thing goes on for infinity, then there are going to be all of us and so on and so forth. But if you really take that seriously, it seems to me that very radical questions are raised about the extent to which you should believe what you take to be the outcomes of your measurements.
That's fair enough.
Because they're given governed by the power law too.
Yeah, no, that's fair enough. I think that it is true that what I will be doing is making an assumption that needs to be justified and has not been, which is that if I open my eyes and take some data, well,
Right.
I think you said it perfectly clearly, but I agree that the assumption that there's a meaningful sense in which, this configuration that I'm experiencing, followed by the macroscopic laws of physics from what was happening 5 minutes ago,
Right.
is something that needs to be demonstrated in a picture like this.
Okay.
And I don't think it has been. So that's a good point. I'm going to assume in what follows that it has been,
Right.
but I agree that it should be. Yeah, that's interesting.
Anthony, sorry.
Yeah.
So I actually have a question. I wonder if this is too selfish, maybe we should just wait to the end. But I mean, I want to go back to the issue about the holographic principle and the entropy balance. So I mean, you sort of threw me for a loop when you said which holographic principles are. I sort of thought that there was this sort of standard way of understanding the content of the principle, its implications and its assumptions, and how you arrive at it. So I thought the idea was there's a kind of universal relationship between geometry and information, and that the holographic principle is sort of telling us that, look, this has to do with the sort of number of fundamental degrees of freedom in your description of matter in space-time. Is that sort of like the idea?
So there's a holographic principle that Tuft devised, which sort of, and I think a lot of these people somewhat think that says it's somehow at least equivalent and maybe even better to think of the degrees of freedom of some volume of space as living on its boundary in some way, or some region of space-time as the degrees of freedom are living on this null surface or something. So I'm not sure it's a principle in the sense that I'm not sure that there's a whole lot of things that you derive from it in a sense. So the Rousseau bound, for example, insofar as there's a derivation, it's a derivation from, say, Bekenstein's bound, which is derived in some sense from the generalized second law.
Well, some people think you can derive it from Einstein's equations, given some assumptions about energy.
Those assumptions about energy are essentially the Bekenstein.
Oh, the Bekenstein. Okay, right.
Yeah. So it's general relativity plus a covariant version of the Bekenstein.
I see.
So, yeah, I think it's one of these things that's a little bit, I'd have to know exactly what version of the hologram, we could talk about any given statement in somebody's paper about what they think the holographic principle is. But I'm not sure that there's something like, it's not like the equivalence principle where there's a succinct agreed upon statement of it as far as I know.
Okay.
So following up on David's question, just to clarify, it seems like if there's only one CMB power spectrum for the whole infinite space, then different copies of you living in different regions would see slightly different realizations of that on the sky. But as David's question is saying, what is to prevent any of them from seeing a realization that's drastically different from one that would lead them to infer roughly the same power spectrum that we do?
No, that wasn't the question. The question was, suppose you take it seriously, not just about the sky, but about the world, okay, that it's determined by the world as a whole, including the material that we're made of, so on and so forth. And we're determined by some probability distribution, okay? That all kinds of different copies of me are going to occur with a certain frequency, blah, 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 just determined by this probability. If that's the case, then it's not clear, first of all, why the brain state I end up with after I open my eyes should have anything at all to do with what's in front of me, okay? With what's actually out there. Okay.
So this is another version of the Boltzmann brain problem.
Yeah.
It's similar. It's also, I think, very related to the what's it called? What do they call it? The problem of time. I guess you could call it the problem of time in quantum gravity, where something like the Wheeler-DeWitt equation just tells you, okay, there's a set of wave functionals that you can have for space-like regions and fields, and it spits out a probability for each one. So what do you do with that? It doesn't tell you anything evolves into anything else. It just gives you a probability for each configuration. And so in order to make that into an account of the world we see, there has to be some argument that things like stable structures and time evolution and stuff emerge from that set of probabilities over configuration.
And that they behave the way we think they do.
Right.
Right.
And I think there's been progress in that, and I'm not an expert in that technical problem of getting that out of the Wheeler-DeWitt equation. I think there are people who feel convinced that they've made progress in that, but I can't vouch for that. I think they've actually answered that question. But it's an open and interesting foundational and technical question that people are working on in that context, and I think you'd have to do something similar, in fact, maybe very similar here to show that. Yeah.
How would you do a sort of comparison between the classical Boltzmann brain and the last two cases we just been looking at? So it seems like even if you take sort of David's point on board, so we need sort of in the classical case some finite period over which we're going to sort of trust our measurement record or something like that. You can still go sort of quite far back and have sort of 100 years of history or something, and then apply the Boltzmann brain scenarios after that. And so that will get you out of the problem entirely. But for the cases we're talking about here, it sounds like such a move isn't available. So you really do have to sort of address this problem of how you're going to get.
Well, I think my first instinct is that this is a much less severe than the usual Boltzmann brain problem, because I think there's no particular reason to expect the second thing that I have to think about whether I want to make this argument.
So perhaps there are other ways of getting out of Boltzmann brain cases we might want to avail ourselves of. I just take it there's no sort of simple way of getting, in the classical case we're taking it for granted that we're going to get some correlation between things arising, whereas here you seem to be even that much in question from the very setup, and it's not clear how we can get sort of some correlation here enough for some measurements, but not sort of to get it down to one entirely. What would happen in the classical case?
Yeah, well, I think it's true that once you assume that there is this infinite statistically uniform space, there's no, then you've assumed it. Sort of like once you've assumed in the Boltzmann brain paradox that there's an infinitely long-lived finite Hilbert space thing. Once you've assumed that, you're sort of stuck. Here, I think once you assume it, I don't think you're necessarily stuck, because I think, but I wouldn't necessarily defend to the death right now, that the second thing that I said, that in the Boltzmann brain, part of the key problem is that subject to the constraints you put on, you should be in a maximum entropy state. Right? So you should see a maximum entropy state subject to what you've specified. I don't think that's necessarily the case here, although I think that needs some demonstrating. But I don't see that that's not a very suggestive conclusion to me. So I think in that sense it's different. I think you do have to account for this, but I don't see an obvious reason why you're going to get wild discord with your observations the way you do in the Boltzmann brain paradox. I'm not sure if I addressed your question.
Can I ask one, sorry to keep going on this, but the thing that seems to be common between these two cases is that you adopt an approach where you reason as if you're some sort of agent outside the system and you're asking about where you're located, either in the Boltzmann brain case in time or in space. And you're asking, there would be many replicas of similar physical systems, and which one is me in some kind of lexical sense. So I just wanted to ask why you think we have to reason that way. Why is it that you have to ask the question that way rather than just saying, we're in a location somewhere, and we're going to, not ask that sort of indexical question?
Well, what are you going to do then? So if you want to make a prediction about what's going to happen next, I mean, if you say we're here, it just that doesn't get you anything. I mean, if all you've got is our statistics over the different configurations you might see next. There's no, and you've got some information. I'm not sure what else you do. You can pick different measures to put over the set of possible observers who you could be, rather than a uniform one. On what basis you would do that, I don't know. But I'm not sure that you have any choice other than to, well, I would just put it there. I don't know what else you would do if you want to make a prediction. I can see that this talk is going to be wrapped up very quickly. So, I'm going to skip this one because we've now discussed what we think about this. Now, one thing, what I do want to do, though, at some risk of it just eating up the rest of the talk, is to talk about this in terms of quantum mechanics. Should I do this? Maybe I should just... This is very, very dangerous. Let me refer you to the following paper. I just think we won't get to talk about anything else. I'm going to refer you to this paper if you're interested in a long 30-page discussion of this question in the context of quantum mechanics. This diagram will make it all clear. You can guess that Max drew this diagram. But what I want to work on, what I want to talk about, so that I fit it sort of into an hour and a half, is cosmology. And in particular, just in the same way that all possible versions of this room is replicated in all possible small variations on this room. If the universe really is infinite in this sense, then all possible local universes are created too, with all different sets of cosmological observables, like the dark matter density and the photon to baryon ratio, and so on. Well, actually, I should be a little bit more careful about that. All possible things will be generated if those properties have some mechanism for varying. So, if it were the case that the amplitude of primordial perturbations were 1 over pi to the 4th Euler number to the Euler number cubed, then this would not be the case, right? But if it follows from something else, which we think it probably does, and that thing could potentially vary from region to region, then we have to worry about that. So for example, the axion, so suppose the dark matter were an axion, there's an axion field in that case. That field can easily vary from place to place, and if the axion field is kind of laid out before or early in inflation, it can get stretched out so that those variations happen on scales larger than our observable universe. So we just see one axion density here, but it takes all different values elsewhere. Or in the sort of picture I was talking about before, where there's a complicated inflationary potential, maybe we tunnel this way and roll down this way. We have lots of e-foldings of inflation, and there's a particular power spectrum and so on. Maybe we tunnel this way and there's a different power spectrum, a different amplitude of perturbations. So there are all kinds of, most of the cosmological observables that we have, there are, if not inevitable, there exist mechanisms where those parameters could change. And so if that's the case, then if we say, here's my theory, I want to go and test it by measuring the observed universe, we have to be pretty careful about exactly what question we ask, because we can't just ask the one we want to ask. That's what we want to ask. What values of the observables will we observe? But that's not on the table if there are multiple possible answers to that question, right? There are multiple sets of cosmological observables coming out of the same basic theory of cosmology. So I think we're forced to ask something which we'd rather not, but we can at least try to do it in a methodologically consistent way, which is to say, given that I am some randomly chosen X, what will I observe? So we're assuming some typicality postulate, and we have to choose an X. So we might ask, for example, what values would be observed in a randomly chosen universe? That seems kind of plausible since we're doing cosmology, but it's, or we could ask what values would be seen from a random point in space. That also seems reasonable. Or we could ask, what values would be seen by a random observer? They're observations, after all, so they should be done by observers. The problem is that, well, then we assume that our observations are those of a typical X, and we can generate probabilities out of this in a straightforward way if we can calculate those things. Now, what's tricky about this is that all of these are somewhat confusing and problematic when you actually try to implement them. Like if we ask what would be observed in a randomly chosen universe, we might say, oh, okay, there's 4 blue universes to every 1 red universe, so it's 4 times more likely that we'll find ourselves in a blue universe than a red universe. But then we have to be really careful. How do you define a universe? So I, split this red universe into 4, and then it's 1 to 1. So I have to have a specific and calculable definition of what an X is. And universe, it's not clear exactly what that definition is. If you're thinking about bubbles, well, bubbles collide and merge and do all kinds of stuff. If you talk about horizon volumes, they evolve. So there are genuine tricky things. What values be seen from a random point in space? This also is tricky because, as I discussed at length, a point in space or a volume in space is an intrinsically ambiguous thing. It depends on your coordinatization. So Winitsky, for example, showed in a fun exercise that if you have an exponentially expanding space like de Sitter space, you can actually foliate it in such a way that the physical volume of the space continually decreases. So you thought it was exponentially expanding, but in fact the volume is getting smaller and smaller. By doing this tricky foliation where the surfaces are almost null, because a null surface basically has no distance along it. It's null separated. So you can do this kind of thing, and he showed this is just sort of this is a stupid foliation to use, but it's a proof of principle that you have to be careful. Yeah.
Doesn't that point to the idea that you want to condition on things that are invariant under coordinate transformations?
Yeah. So certainly this is in empty de Sitter space. This is an unpleasant thing to do because it clearly is non-invariant. I don't know. Ambiguous. So yes, I think that's a potential lesson. If you talk about a random observer, well, what's an observer? This is the kind we know about, but I always like to think about this guy who might be orbiting, a black hole and made of neutrons and so on. Or, we can worry about these. So I think there's a tricky, we'll get to the tricky aspects of this, but we can nonetheless try to go down this road. So this is a road that we might not want to go down, but I think once we accept that the universe may be infinite, then we have 2 choices. We either have to sort of say, okay, it's not, I just want to say the universe is not infinite in a sense. Or I think you're forced to go down something like this road and think about these issues very carefully. So what might we do? So how would we actually calculate this probability distribution? I'll call it piece of x of OI. So the observables are OI. Those are some things that I might measure, like the 6 cosmological parameters. The x is the thing that I've used to count it. So I want to know pxOI, which is the probability that a randomly chosen x observes those values out of the possible set of values of those things we have. So here's some steps that you might take. Choose your x. It might be, for example, a stable solar mass star with solar metallicity. That's my proxy for an observer. Count those up. Then that's not something you can really calculate in general directly from like an inflationary Lagrangian. Just methodologically, you generally have to you do something else, like choose some counting object, maybe a cubic centimeter of physical volume at the time of reheating. So that's something you can sort of calculate from the dynamics of inflation. And you can say the probability for x of a given OI is related to the probability of those cubic volumes by the number of x's you get per cubic volume. Then you can calculate the counting thing, p sub p, using the fundamental theory of inflationary dynamics. And then you can try to calculate the number of x's, say solar mass metallicity stars per cubic centimeter. So if you could do all that unambiguously, you would have a prediction for p sub x of O sub I. And so a case study of an argument like this that's been made is what I'll call the Weinberg-Banks-Lenkin argument for cosmological constant. Weinberg was the first one that made it vaguely in the literature. Tom tells me, and I'm sure this is true, that he sort of maybe not made it to Weinberg, but knew it before Weinberg and told Weinberg that he agreed. Vilenkin made it more precise with an actual calculation. So the idea is, let's take our counting object to be a baryon. Okay, so we're going to count up baryons. And we're going to say the probability of a randomly chosen baryon being in a universe with cosmological constant lambda is independent of the cosmological constant. It's a flat probability distribution. Now this seems like kind of a really strong assumption, but Weinberg argued, and I think reasonably, that to assume something else would mean that you have something correlating the existence of baryons and their production to values of the cosmological constant. This is very close to being a solution of the cosmological constant problem. That is a priori impossible to come up with, and therefore this is a good assumption. I was joking about the a priori impossible part, but those of you who know about the cosmological constant know that it's a famously hard problem to solve. Yeah.
I mean, we're sort of trained to be skeptical of an argument that says, oh, we can't talk about a correlation between x and x, so we should apply equal probability distribution cost or something.
Yeah.
Is there more going on here than that, or?
Well, a little bit. So a slightly fancier version, well, slightly better really, is to say that although this is not the version that Weinberg uses, this is more what people use nowadays in thinking about the string theory landscape, is that they say, well, actually, the different values of lambda are coming from sort of just cancellations between a bunch of contributions to lambda that happen due to the different values of the fluxes in these compactifications in the string theory landscape. And you're using this big, and basically all that's happening is they're canceling in various ways to give you a spread of possible values. Now, the physics that's determining the values of the vacuum energies from those different fluxes is at super high scales like the string scale, and is expected to be very decoupled from the somewhat lower energy physics of even baryon production, but certainly like stars and galaxies and cosmological expansion, things like that. So the argument there is more that there's a real hierarchy of scales such that it's hard to see how there'd be any connection between a particular very fine-tuned value of the cosmological constant and these things. And or another way to look at it is that if you want the value of lambda to vary sort of on scales comparable to what we see, like from our value to twice our value and a quarter our value, that we know is like a fine-tuning of a part, you know, in 10 to the 120 or something of the scales over which it varies due to the fundamental theory. So you have to somehow get that 10 to the 120 in there in a way that connects with the baryons. And if you could do that, again, you'd have sort of a solution to the cosmological constant problem, because you've gotten the 10 to the 120 in there. So maybe it's a similar argument. There's a little bit more behind it than flat. So then the argument goes, let's just vary lambda. And as Joel cautioned you, this is a dangerous thing to do, but if we do it, keeping, for example, the perturbation amplitude Q, that's a thing with 10 to the minus 5 in our universe, and the photon to baryon ratio C and other cosmological parameters fixed. Now let's let X, the object that we're saying we are one of, is a 10 to the 12 solar mass galaxy. Why do we choose that? Well, it's something you can calculate pretty easily in using standard cosmological things. Obviously, none of us is a galaxy, but we do live in one. There's a bit of circularity to this sort of argument, but this is the argument that they're giving. Then what you can show, and specifically, I think what, does the light can show that in that paper? Might have, but it's true, that what you get from the theory of structure formation is that there's an exponential cutoff in this parameter, lambda over c to the fourth q cubed, that basically arises from the fact that if lambda is too high, then structure formation shuts off before you ever make galaxies of that mass, other than in this exponential tail of the Gaussian fluctuations, and that's where the exponential comes from.
That's not an n, that's a lambda.
This is a lambda divided by.
Yeah, okay.
Sorry about the font.
That's all right.
If you fix c and q to be the values that we see, you find that this probability distribution peaks relatively close, maybe a few, maybe 10 times higher than the observed cosmological constant. Now, I think it should be noted that Weinberg actually used this argument to predict that there would be a small but non-zero cosmological constant before it was measured. So that's the best kind of prediction, right? And he did make that based on this argument. And if you want to see the turgid details for axions, that's that same paper that no, this is a different paper. This is the paper that you can look at. So this is a case study. Now I want to go through some of that's sort of an example of how a calculation like this might look and has been done. But I want to talk about some of the problems that you run into when you think carefully about this sort of calculation. Especially when it has to do with other parameters that it may not be so clear that you can pick, for example, a flat probability distribution. So one hard thing is, what do you choose for x? You don't know exactly what an observer is. You do know that if you assume that we're typical observers, you get other paradoxes you have to worry about. So for example, many of you have seen this, but it's a fun one. Suppose the thing that we want to observe is the number of observers born before us. Now we have two theories that we want to compare. One in which, this is the kind of hopeful one, where here the population has been growing, it's like, what, 7 billion now. Somewhere around here we solve the ecological mess we're in and leave the Earth and populate the solar system and the galaxy and so on. And the population just keeps growing. The pessimistic and unfortunately more realistic perhaps one is this, where the global ecological catastrophe happens, or we blow each other up, or whatever, and the population precipitously declines. Now, we want to compare these two, so we say, well, if I'm a typical observer of all observers that exist, then it's really, really strange that, that a typical number of people born before me in this theory is some really big number. It's huge. It's like gazillions, trillions, whatever. In this model, it might be 10 billion, and that's what we observe. And so I should believe this model over this model. And this is the so-called doomsday paradox. What's strange about this is that you've made this pretty important prediction about the future of humanity, not based on the chances that we're going to stop global greenhouse emissions or tie up all the loose nukes or whatever, but rather this weird kind of anthropic argument. This seems like not the right way to predict the future. There are other things that are disturbing about it. Actually, if you want to be less disturbed, I did the calculation. In fact, humanity has been around for a long time. It turns out that if we stabilize the population now, we could go another 400 years or so before we start to run into this argument. So it's not even that soon of a doomsday. But anyway, I think that is not the right resolution of the argument. So it leads to, so this methodology leads to some strange conclusions that we may not believe. Another fun version of this, has anyone seen the Adam and Eve paradox? This is a good one. So Adam and Eve are in the Garden of Eden. This is a related paradox. And there's a serpent. And Adam, for weeks, has been kind of making more and more advances towards Eve, which she has been kind of fending off. And the serpent comes to Eve. And the reason is that, you know, Adam says, nothing bad is going to happen. Eve says, but I'm worried, you know, what if I get pregnant or something like that? It could be dangerous, there's no hospitals around. So the serpent comes along and says, look, Eve, don't worry. Don't worry. Because there's two possible things that can happen. One is that you get pregnant, you have children, your children have children, they have children, the population explodes like this. Okay, that's one possibility. The other possibility is you and Adam go at it, but nothing bad happens, like you said. Now, what are the chances that out of all these people, you would just happen to be the very first ones? That's ridiculous. So this can't be true. So go ahead and do it. So here we are. Another possibility that's been bandied about in literature, and I think is tricky also, is the so-called, actually some people call it top-down and other people call it bottom-up. But the idea is to say, I am an observer whose name is Anthony and is a cosmologist and is in a room with a desk. So to condition on every possible thing we know. So take it all. I know that the cosmological constant, you know, in terms of the critical density is 0.72, 3. So put that in. So fold all that stuff in and then make some prediction. Now, I think what's very tricky about this is that you have to be careful because it makes it very hard to rule things out. Right? So here's my thought experiment. That on Monday, here's theorist A, who says, according to my doubly quantum supertorus theory, there's an almost unity chance that the universe will be red and right spinning. There's a tiny chance that it's blue and left spinning. Okay? So this is the prediction he makes. On Tuesday, the universe is observed to be blue, seemingly contrary to his prediction. But then this guy comes along and says, don't worry, it's okay. I'm just going to use top-down reasoning and assume that the universe is blue. That's a given. And then I'm going to use supertorus theory to say that the universe is left spinning, because that's the prediction of supertorus theory, that it's blue and left spinning. And I see that it's blue, so it's got to be left spinning. And then Thursday, the universe is observed to be right spinning, but then you can see that we can repeat the process as much as we want. So once we've admitted that we're going to wave away seemingly incredibly improbable things by just conditioning on them, then we have to be very careful, because what happens when the next very improbable thing happens? Why do we either have a basis or no basis for waving away that thing? Right? So I think the conclusion of this for me is that you have to have some sort of rationale for conditioning on the things that you're conditioning that doesn't just allow you to willy-nilly accept seemingly incorrect theories by conditioning on them. Okay, so that's all I'll say about the thorny conundrum of picking an X. I'm not giving you answers to these questions, obviously. Just the questions. Now, another question is, so if you've chosen an X, how do you compute this counting object? The probability that it randomly chosen, say, baryon, or volume of space or something, is in a universe with observables close to high. And here, I think there's a lot of bad news, because you might initially have thought that this was something that would just be pretty straightforward to calculate, but it's not. The reason is that, as I mentioned, if we think about bubbles, for example, there are infinitely many bubbles, each one is infinite inside. And so to do any sort of counting, you're comparing infinities. And there's a nice statement of this paradox that goes, you know, it's not often you get to reference somebody from 1638. But this was first posed, I think, pretty sure it was first posed by Galileo, who said, you know, you might think that there are just as many even numbers as odd numbers, right? Because you can say, here's an even number, here's an odd, you can make a one-to-one correspondence. But you can also make just the same one-to-one correspondence between odd numbers and all integers, or between any set of numbers and any other set of numbers that you want. And so it's very difficult to say there are as many evens or odds, or there are more integers than regular numbers, and so on. And in modern mathematics, this is just taken as sort of part of the definition of infinite sets, that if the sets have the same cardinality, like these are both Al of 0, then that's all you can say. They're both Al of 0. And the obvious answer, so that's the bad news. The bad news is that mathematics is not going to help you with this. It's going to tell you they're both Al of 0. At the same time, there is an obvious answer. When we say there are as many odd numbers as even numbers, we have in mind, well, let's start at 0 and start counting the numbers up to n, find the ratio, and then send n to infinity. So that's a prescription that gives a well-defined answer. Right? Once we've chosen that that's what we want to do, there's no ambiguity as to what the answer is. And it seems like a reasonable one, and it's taking into account the fact that there is an extra piece of information around, which is the ordering of the integers. Right? There is an order that they have, and that's, if they were just randomly ordered sets, they were just sets in bags, we wouldn't have that, but we do have the order of the integers. Now, the unfortunate thing, so people, when they started thinking about this in cosmology, figured something similar would happen. If we use something like volume, pick a point in space, get bigger and bigger spheres of volume around it, that they would converge to some unique and unambiguous ratio for these infinite, so for the ratio of these different infinite quantities, just like with the images. The problem is that in eternal inflation, the answer completely depends on the way in which you do this cutoff procedure. And a way to see that, I think, I call this the domino dilemma, but I think recently it's been called the Guth-Manchurian paradox. But I can tell in an actual dialogue by myself and Alan Guth, you can decide which is Simplicio and which is Sagardus, or whatever, for yourself. So this is a literal conversation we have. So Alan Guth says, imagine you have the universe is dominoes. And in each instant, you line up, so here's the universe, it's made of a 1. Then at the next instant for each 2, that's kind of a slightly older part of the universe that evolved from 1, it creates 2 new bits of volume. So this is the self-reproduction of an inflationary universe. And then each of those 2s creates 2 new volumes of 1, etc. Okay. So then, let's ask, okay, are we a 1 or a 2? Is our observed universe a 1 or a 2? So I say, okay, let's take a slice through this and count up the 1s versus the 2s. We see there's 1, 2, 3, 4, 5, 6, 7, 8 1s and 4 2s. So there's a 2 to 1 chance that we're a 1. Right? 1s are twice as probable. But I say, but every 1 comes with a 2. I mean, by construction, every 1 has a 2. So how can there be twice as many 1s as 2s? That was like the law of physics. 2 follows 1. Cruz says no, I say yes, and that goes on. So the problem is that, why is this happening? If I just put a bunch of dominoes here and counted them up, you would find half as many 1s as 2s. If you put a huge array of them and started doing spheres of dominoes, you'd find approximately half as many 1s as 2s, and it would converge to a half. Why does it converge here? It doesn't converge because it's exponentially expanding in this direction. So it's always, the total number is dominated by, well, let me say it a little bit differently. What you've done here, so another way you could do this is you could actually just integrate everything up to here. Okay? If you integrated above here, you'd find not 50-50, but you'd still find a predominance of 1s, and you can see that because what you've cut off mainly is 2s. So if you integrate up to here, it totally depends on, the problem is that it's totally dependent on the distribution at the cutoff surface, which is here, rather than in the volume, which is up here. And that's a generic property of eternal inflation, that the kind of latest times have exponentially well, the latest times have as much volume in them as all earlier times put together, so you never get to a convergence by being able to ignore the surface. And if you allow yourself the freedom to choose your time surfaces differently, you can get any value you want. You can get all ones, or half ones and half twos, or any combination, all twos, whatever you want. So there's a real ambiguity because it depends on the cutoff surface, and there's no unambiguously chosen cutoff surface. So what do people do? So people have tried to say, all right, that's annoying, but let's just try. Let's put some sensible measures on these huge but finite regions and see if they converge, and make an argument from some reasonableness or simplicity criterion that those are reasonable things to try, and see what we get. And there are lots of different choices for that. There's a few basic sort of philosophies behind them. You count physical or co-moving volume or volume created, so sort of volume-based ones. Ones that count numbers, like numbers in pocket universes. Another set of things that take, rather than volumes, take a particular world line and look at what happens, what sort of regions this world line passes through, so world line-based measures. Other ones kind of project everything up to future infinity and do things up there. Now the interesting thing, I think, is that, well, there's two interesting things. One is that all of these have various fairly to very major issues with them. So the Boltzmann brains affect some things. There's a Young's paradox. There's a fast transition fiasco. I'll call it the Q catastrophe. This one I made up transition upside down. It's the domino dilemma you saw. Observational obstacles to equal wave. So all of these, in some sense, entail results that seem to be arguably, and literally there will be arguments, lead to results that are inconsistent with various basic things that we see. And at least a lot of them can be eliminated on this basis. In other words, if this fundamental theory is correct and this measure is the right one, then that does not describe our actual world. We buy this whole methodology. So let's go back to the drawing board and pick a new measure. So many are ruled out. Another very fascinating thing that's happened is that many of these measures that people have come up with independently have turned out secretly to be the same measure. There was this nice paper by Linde showing that like 4 different measures were the same. There's a paper, 2 of the most popular ones were shown recently to be basically the same measure. Not in that they were obviously the same, but you could show by a fairly complicated duality argument that they actually are the same. So you might hope that we're running out, that there are only finitely many plausible and reasonable measures. Plausible and reasonable are important there because the actual cardinality of the set of measures, I believe, is LF2, which is probably the biggest set anyone seriously contemplated trying to pick things out of. So maybe, it could be that the community kind of converges on, there's a measure which is nice and lots of people like it, and it gives results that are in accord with what we've seen so far, and seems free of weird paradoxes and self-contradictions and so on, and everyone says, yeah, maybe that's the right measure, or maybe not, and I don't think we're quite there yet. Maybe where we are is people get tired of working on the measure problem and stop. Case in point. Leaving only the very diligent to keep on. So we've covered picking an x, we've covered picking a way of counting p's. So what's left is counting the number of x's per p. The good news is that that's something we can actually do. Joel gave a very nice summary of sort of how we make cosmological predictions from, and Matt too, from a basic cosmological model like one specified by the standard 6 cosmological parameters. Here are very outdated values of those parameters from 2006, but in a nice form. So dark matter density, say, baryon per photon ratio, cold dark matter mass per photon, neutrino mass per photon, scalar fluctuation amplitude. One thing that's important in this game is to think about dimensionless parameters, because saying omega of 0.7 means absolutely nothing when you're comparing different universes. You'd have to make a whole bunch of other specifications. But saying 10 to the minus 5 is meaningful, these ratios are meaningful and so on. So you have to get the right variables. The Hubble constant, notice, is not one of these. That's not something that specifies our universe. That, in some sense, specifies what time it is in the universe that we're seeing now. It's an important thing to measure, but it's not something that determines our universe. There are a bunch more optional ones. Some of these would now move from optional to mandatory, like the scalar spectral index. We know what it is now. It's not one. Most of these, this one might actually have some anthropic connections and so on. So there's some more optional ones. And then there's all of particle physics. 20 odd parameters of the standard model of particle physics, plus neutrino masses. So that's hard, but if we focus on these, it's actually a fairly doable problem. So if you wanted to do this, you could take, for example, one of Joel's semi-analytic codes and put all these things in. I would be a little nervous about it because they've developed it to work in local variations of the parameters we see. And I'm not sure, without a lot of reassurance from Joel, that I'd want to push it to orders of magnitude different. But some of the things would work. Max did a very nice job in that paper of doing a sort of analytic version of this. So here is the fraction of dark matter collapsed into halos above virial temperature T-vir in terms of the photon to baryon and dark matter to baryon and amplitude of perturbations and the density and the proton mass and all this stuff. It's all there. In gory detail. Whoops. Okay, that's all you get to see. So there are lots of interesting plots that you can see from that paper that sort of show you the way, for example, this anthropic argument of that originated with Weinberg works out in terms of the actual observable. You have to do some, so that's part of the problem, that's counting dark matter halos of particular properties. And to turn those into galaxies with stars requires a whole bunch more detailed physics. That's actually where Joel's codes would be more useful than in the dark matter halo fraction we can do pretty well. But this is hard. But it's doable. This is all physics that we in principle know. And there are questions with answers. So there is an answer. So once you specify X, that it's a stable star with stellar metallicity, it might be hard, but there's no fundamental obstacle to being able to calculate that from the cosmological parameters, whatever they are. Let's see, what I want to note. Yeah, so some of the things you would find that are interesting in terms of making these anthropic arguments are, for one, the cutoff at high cosmological constant because structure formation gets suppressed. And then people have argued that at high and low density, you run into issues at high density because solar systems wouldn't be too stable because they run into each other too often. At low density because it's hard to get things to cool sufficiently to make stars, and then even if they do, you'll often unbind things before you can build up a nice solar metallicity halo to build solar metallicity stars. So the good news is it's computable. The bad news is the results you get may be complicated and you may not like them. In particular, as Joe mentioned, and I talked about before, there are degeneracies in these cosmological parameters. For example, this halo fraction depends on this thing, so it's this ratio of lambda rho lambda to rho star, where rho star is this thing. So you can see immediately that you can just trade off C and Q and rho and get the same value out of this thing if you do it in the right combination. As well, qualitatively, new physics can change the simple reasoning you might have. For example, Joel mentioned this paper that I came up with about a cold universe where stars form by a completely different process than they do in our universe. There's one by, this is not cosmological parameters, but it's a kind of fun paper, imagining a universe where there's no weak interaction. That turns out to cause some problems, but they're fixable. You can come up with fixes to the changes. Yeah?
Have you ever thought about lower bounds on lambda? Because you could have too many galaxy mergers, and that would be...
I don't think you could get a strong lower bound, because most of star galaxy formation has happened now. I mean, I think if you just took away our cosmological constant, the future universe would change a lot, but the present one would be terribly, terribly different. It would be different, but I'm not sure you'd get any major anthropic effect.
Well, let's say the galaxy merger rate at earlier times was 10 times higher. That wouldn't necessarily have any effects for...
That's nothing to do with lambda. Lambda wouldn't affect that.
You need a bigger amplitude of perturbations or maybe dark matter to photon ratio or something to do that.
Because a small lambda wouldn't affect structural formation that much.
Right. I mean, yes. Yeah.
Yeah, I mean, if we're talking about the value of lambda rather than the absolute value of lambda, then surely there's some sort of lower bounds if you had.
Oh yeah, no, that's certainly true. That's certainly true. So for negative cosmological constants, there's a lower bound from the universe lasting long enough to get.
Yeah, I'm talking about the lower bound that's still positive.
Yeah. No, the way that and I didn't mention this, but the way that the anthropic argument works. So you might say, how did Weinberg get something like R value if there's only an upper bound? Right? And the way that it works is if you assume a flat prior for values of lambda, right, then in log lambda you get pushed towards higher values. And so that rising prior in log lambda with the cutoff is what gives you something that's comparable to what you're seeing. So the downside of this is even if you make a prediction like I'm going to anthropically predict lambda, you might do it and be like, yay, I predicted lambda and I got it right and I explained lambda. But then as soon as you add some other parameter and allow it to vary, that prediction may well just completely disappear. And so you really have to, if you want to do this seriously, so for example, the Weinberg argument falls apart if the sort of prior probability distribution for C and Q is rising. So if higher values of the perturbation amplitude, and this is quite plausible, or photon to baryon ratio, which is maybe less plausible but possible, are favored, then the argument just doesn't work. So if you want to do this seriously, you have to be careful because many of these successes that you might see touted are fragile and provisional, depending not just on the prior probability distribution, but choices of which parameters you allow to vary and so on. So in summary, and only 3 minutes too late because I skipped the whole fun part, is I think either infinitely or finitely many states in the universe create sort of uncomfortable issues. The infinite statistically uniform spaces many claim to be create uncomfortable issues. Infinite production of different cosmologies with different properties creates uncomfortable issues. We might have to get comfortable with being uncomfortable. Thanks.
I had a question about the top-down reasoning problem that allows you to allow theories. It seems like you had a case where you had a different understanding of probability, so I thought you were saying like it allows you to condition on improbable theories and therefore avoid refutation. But it seems like the case you imagined, you had something like a quantum mechanics case where you're just given a stochastic evolution that gives you definite probabilities. And I thought there's an issue about how that kind of introduction of probabilities compares to the probabilities that you're assigning over values of cosmological parameters, right? So it wasn't clear to me that the refutation you gave was, I mean, it seemed to involve two different notions of probability.
Yeah, so let me try to be a little more clear. So so one might say, if you see that the, let me try to think of a good example. So suppose you want to predict what value should be seen in some theory for the cosmological constant. Your fundamental theory might say, well, you know, flat distribution over cosmological constant, so we would expect to see some really huge value. And maybe some flat distribution over the up to 1 or so of the amplitude and density perturbations. Now, if you use both of those, then you would say, okay, what we really predict probably using this methodology is a very high perturbation amplitude and a very high cosmological constant. So do we rule that theory out? So someone might come along and say, well, if we want to just predict the cosmological constant, shouldn't we use the information we already know? We know that the perturbation amplitude is 10 to the minus 5. So let's use that and predict the cosmological constant. But so my question is, where's the justification for conditioning on 10 to the minus 5? It's true that that's what we see. But in doing so, you've implicitly accepted that we are, in some sense, in this very rare region of probability space, because the predicted probability was very small to see 10 to the minus 5. So once you've swallowed that we sort of live in some unlikely corner of probability space without providing any real reason for that, then how do you believe anything else? Is I think the question I'm sort of getting at. You've assumed in some sense that you're either very atypical or that there's some reason that we're in that region of probability space that we haven't figured out yet in our theory, but we're not going to use it for anything else. So both of those seem like a dangerous thing to me to do. I'm not sure if that helped.
Yeah, no, I thought the kind of argument that you gave was more clearly somebody doing something that was just obviously wrong in the way they were reasoning. Whereas in the cases you described, I think it seems more plausible that you'd throw up your hand and say, well, I don't really know how to assign probabilities to this sort of situation, or perhaps my fundamental theory doesn't really ground probabilities for these parameters in a way that's as rich as the way it grounds probabilities for things like, you know, doing experiments with quantum mechanics.
Certainly it doesn't, but my answer is the same as to your earlier question of what else you can do.